Hello and welcome to another lecture. So we're gonna look at the Riemann mapping theorem finally, and this is section 6.3.1 or subsection 6.3.1 in the book, and you can get the book in the link in the description. It's free online, or you can get a paperback. All right. So what does the Riemann mapping theorem say? It really says that up to biholomorphisms, the only simply connected domains in C are C and D. Right? And if you generalize this to manifolds, you're also going to get the Riemann sphere, but that's it. So, all right, so more precisely, it says a little bit more. So suppose that I have a simply connected domain such that U is not the entire complex plane. So the entire complex plane is simply connected. But let's just suppose U is not that, it's any other simply connected domain, and let's pick a point in U. Then there exists actually a unique biholomorphic, so we also call it conformal map, F from U to D, such that takes P to 0 and the derivative is positive. And by that, the derivative is complex number. How can it be positive? I just mean that it's real and positive, right? That's what we mean here. And there is actually a unique one that does that, right? Basically, you can. I mean, it's not hard to to make this work. Once you have a mapping, you could always apply an automorphism of the disk, and then you could rotate, right? But of course, the interesting thing was going to be unique, and we're actually going to use these conditions. They're not just sort of extras, but we're actually going to use that to construct this mapping. It's really this sort of maximization, this optimization problem that we're going to use Montel's theorem for. All right, so let's just see an example. So if we have the upper half disk, and we pick this point P. And the reason why I did that, because I knew what the map there was. So it will take this point to the origin, and you can see where it takes these lines, right? And it works conformally, so all the angles are preserved here, right? So that's the way the map works, right? Now, the point is that the way we're gonna find this map is by trying to maximize the derivative at P, and then to make it positive and real and positive, that's just going to be a rotation. So we're just going to first try to maximize the modulus of f prime at P. And that's actually, among all the maps that go into the disk, right? So, and then take P to 0, right? And the maximal one, which we're gonna get by Montel, that's this one, right? So, well, we have to prove that that's what it is, right? So, but that's the idea, right? And so the idea is that we're really trying, like, how do you how would you think that you're going to fill the entire, so you can always maybe, well, that's going to take a little bit, but that you can always put your U in into the the disk somewhere. You sort of shrink U, like think of U as some bounded domain. You could shrink U and you could map it into the disk, right? Well, how do you make sure that it's sort of like that the map actually expands U into all the disk? Well, you could try to think of, well, I'm maximizing the derivative as, if you want to get as far as possible in the disk, well, it's best to start as, running as fast as you can, right? Have the largest derivative that's going to sort of spread out f as much, or the image of f as much as possible. That's sort of the reasoning, well, like intuitive reasoning behind it, why this why you would think that maybe this would work, right? And it does. So, but we have to prove that it does, of course. All right. So here's just I've just restated the theorem, and so we're going to look at a certain class of functions. So this or certain family of functions, right? F, script F, is a set of injective holomorphic functions from U to D such that f of p is 0, right? And this is the class, this is the family that we're going to try to maximize the derivative over. All right. So first, we need to prove that f is not empty. I mean, if it's empty, we can find the one that the maximizer, right? I mean, if U was bounded, it would be easy. You just sort of shrink U and map into D. So that's easy. But U could be really big. It could be unbounded. It's just not simply connected, and it could be it could be like a slit plane, right? So it might not even have any open set in the complement, right? So it's a little once you start thinking about how you would do it, it's not obvious. But we have to find at least one function in script f. Okay, so it's not the entire plane. So there exists some q that's not in U, right? We look at the function z minus q. That's something that's never 0, right? Because q is not on U, right? Because q is not in U, right? So and we have a simply connected domain, so we can take a square root, right? So the square root. So there exists a square root g, right? So there's a function g such that if we square it, we get z minus q, right? Because U is simply connected and because q is not in U, right? All right, so now let's look at, let's suppose that g, I mean, we're looking for injective maps, right? So g at z is the same as g at zeta. Let's see what that implies. Well, if we square it, square the same number, we of course get the same thing. But that means, right? I mean, the g squared is z minus q, right? So this is z minus q, zeta minus q, right? So z is zeta, right? So therefore, g is injective. Now, might at first seem weird while we're looking at this, but let's look at this. Let's suppose that not just that g of z is g of zeta. Well, what if g of z is minus g of zeta? And the weird thing is, we get the same thing. So z is zeta. But if z is zeta, then this can't be true. I mean, unless g was 0. G is never 0, right? Because g is the square root of a function that's never 0, right? So that's a contradiction. All right. So what does that mean? That means that the image of U under G is actually disjoint from the the negation of that set, right? And by that I mean I just mean like whenever Z is in G of U, I mean minus Z, right? So I just take the negative of all the things in G of U, right? So I have an open set. Minus G of U is open, right? It's basically just as big of a set. It's really, there are two kind of equal sets, just reflections of each other, right? Oops, sorry. So, all right. So that means that the complement of G of U has an open set, like contains an open set, right? We've used this argument before, by the way. So there exists some disk inside the complement of G of U, right? Because minus G of U is not in G of U, and minus G of U is open, right? So, all right. So now, basically, we sort of like once we have a disk, we can move it, move the center to infinity and sort of rescale, and we get a mapping into the disk. I mean, we've seen this before. We've seen this argument before, right? I'm trying to get a bounded mapping, right? So, all right. So once we have that the complement contains a disk, by mapping this to infinity and rescaling, we can get a mapping into D, right? So this mapping Z goes into here, and that's actually the mapping that we're really interested in. Well, almost, but it takes it takes it takes U to D, and then you can compose with an automorphism to make P go to 0. Just again, that's easy to figure out. So we have a map in F, right? So F is non-empty, and maybe I should, obviously, if G is injective, that's also injective, so it's still injective, right? All right. So that's not hard, right? And you can see where existence of square roots is important here, and we're going to use it once more. So okay, so we have that that script F is non-empty, right? So now we can start thinking about applying Montel, right? Because we have a family. We're going to need a normal family. Yes, that's easy. They're all bounded. They're all going to go into the disk, right? All right. So, so Montel will tell us that if we have that we can find a mapping that maximizes the derivative, right? But it doesn't tell us that that's onto, right? So what we have to prove now that if the map is not onto, then we can construct something with a larger derivative at P, which is also in F. So basically, that says that the maximizer will be onto, because it couldn't have been not onto, right? So let's suppose that F is in F, in script F, or F is in F. So F is in script F, but it's not onto, right? So the image is not all of D. All right. So suppose, well, it's not onto, there is at least one point which is not in there. And let phi sub q, that's just going to be this automorphism, z minus q divided by 1 minus q bar z. That's the automorphism that takes q to 0, right? And we'll take 0 to minus q, right? And right. So so we have so once we have this, basically it's q was the point that was not in the image of F, and we're taking it to 0. So therefore, F composed with phi of q is non-zero, right? Okay, well, if F composed with phi of q, right, is non-zero, then it's, again, U is simply connected. There exists a square root, right? And you can easily check that. Well, I mean, if F went into D, this guy F composes phi of q. That goes into D, and square root. I mean, if I have square root of some point in the disk, it's still in the disk, right? All right. Now, if I have if g of z is equal to g of zeta, well then what does that mean? If I square that again, just like before, right? I get that it's true for the squares, therefore it's true here, and these guys, F is injective, and automorphisms are clearly injective. So that means that this is injective, right? Therefore, G is injective, right? We have that Z has to be equal to zeta. All right. So now define H. Okay, this is going to be the thing that was larger derivative. So this H is, well, let's take this G, which is the square root of this guy, right? And let's compose it with phi, but now we're taking G of P to 0, right? So what does that what will that do? That will take P to 0, right? Because G will take P to G of P, wherever it takes P, and then the phi of G of P, well, that will take it to 0, right? All right, right. So that's what we have, and it's clearly injective as well. I'm just composing with an automorphism, right? And another way of writing G is, well, what is the inverse of phi? It's actually phi of minus G of P, right? So I can also write G in this way. Okay, so let's differentiate this equation at P, right? And let's recall that if I have phi sub a for any a, and I differentiate it and set z to be 0, then I'm just getting 1 minus the mod of a squared, right? So that's just a direct computation from this form, right? So what we get is, well, if I differentiate this side, I get this, right? That's just this, right? That's the just chain rule, right? So I get right, f of p is 0, so I have phi prime and q at 0, and that's just this thing, right? Now, on the right-hand side, I have g squared, so if I differentiate that, again, by chain rule, I get this, 2 g of p, g prime p. And so now, okay, so now you have to, unroll the definitions. Let's leave this guy here, right? And so I could differentiate this thing, right? If I differentiate the g, right? And I'm getting, again, by chain rule, I'm getting this guy, right? And h at p is 0, so I'm really plugging 0 out here, right? So we get from this, right? We get this guy, right? That's just the same computation again, right? So we will get that this is equal to this. Or I could solve for the derivative of, well, let's just take the absolute values here. We're all interested in the moduli, right? So let's take the modulus of both sides, and let's solve for the modulus of f prime, right? And you just divide by the 1 minus q squared, right? And you get it's f prime at p is this funky constant times h prime at p. Now, if you do a little bit of you have to be a little careful. Like, notice this square, and there's no square here, and there's this minus plus. But you basically just work out what this is, right? And it will again turn out to just be this, right? That's just what it is, because g g squared is just this thing, right? So if I plug in p, right, to g, I get minus q, right? So therefore, I get get these guys, and then there's a little bit of canceling, right? This is going to be 1 minus mod q squared, as 1 minus mod q, and so this 1 minus mod q squared, you can write it as 1 plus mod q times 1 minus mod q, and and this, so that cancels, and then you're left with 2 square root of mod q. Okay, well, there, it's just a little bit of algebra. But Q, well, Q is something in a disk, so mod of Q is less than 1. And then it takes a little bit of maybe calculus, or it's to show that if mod Q is less than 1, then this thing is also strictly less than 1. Okay, so I'll let you sort of work it out. That's a elementary calculus maybe, right? And so the point is I'm multiplying by uh, something less than 1 to go from h prime at p to f prime at p. So therefore, we have that h has a bigger derivative at p than f, right? We're not necessarily saying that h is onto, right? So we started with f is not onto. Like, we have no clue about h, but h is definitely in f, right? So if you have something that's not onto, you can construct another mapping which might not also be onto. Who knows? But it's going to have a bigger h prime. All right. So now you apply Montel, right? Well, I mean, you could have already applied it, but you wouldn't know what what it gives you, right? So construct a sequence, right, where the limit of the derivative at p is the supremum overall the derivatives, right? And we know that exists by Montel, right? These are all bounded, so you just you can just get arbitrarily close to the supremum, right? And it's still not going to be infinite, because there is going to be, there's going to be a limit by Montel. So, at this point you could assume it's infinite, but it's not going to be infinite. So Montel says that there exists a convergent subsequence. So also generally, suppose that this guy actually converges to some function f. Converges uniformly on compact subsets, right? That's the convergence. And all the derivatives converge uniformly in compact subsets. In particular, they converge at at p. So we definitely get that the fn prime at p converges to f prime at p, right? So by the so now we have this limit, right? So all the fn's are in f, so they're injective, right? Now a limit need not be injective, but by Hurwitz it's either injective or constant, right? So that's a very strong statement. I mean, if it's not these were not holomorphic, you wouldn't have that. But okay, so it's injective or constant, but it cannot be constant, right? Because we know that there exists, I mean, f prime at p for anything in f is positive, right? So therefore the maximizer is positive, right? So we know that f prime at p is strictly positive. It means it's not 0, right? So f can't be constant. So that means it has to be injective. So this maximizer has to be injective. It still takes p to 0, because everything, it's just a limit of functions that take p to 0, right? And now just if you run the limit, so all the f of z in modulus is always less than 1, because it goes into the disk. Now in the limit, okay, so you might get a non-strict inequality. If these were just smooth functions or something, yeah, that's what you would get. But here we have holomorphic functions, so we have open mapping theorem. So f, we know that it maps into some open subset of D, right? So we cannot go onto the boundary, right? It cannot have values on the boundary on the disk. So we know that it actually f of z is strictly less than 1 for all z in u, right? And what we just argued, f must be onto, because if it wasn't onto, it wouldn't have been the maximizer. There would be an h in f with a bigger derivative. What we know that it's the one with the maximal derivative, right? It's the supremum over all functions in f. All right, uniqueness is left as an exercise. So at this point, you don't have that it's necessarily positive. You might have to rotate, so multiply by e to the I theta, and to really get the f from the theorem. And then its uniqueness, I'm just gonna leave it as an exercise. It's not hard. So that's an exercise. The existence is the hard part. And usually the existence is the is really the big deal. The uniqueness, okay, that's just you know um, that's easy to do by methods that we proved a long time ago. But you know the existence, that's the thing that really required Montel. All right, now this theorem is, I mean, one use for it, like if you read a topology book, they might cite this as say, well, any domain, any simply connected domain in the plane is homeomorphic to a disk, right? And they might say, well, it's just by the Riemann mapping term, even though they only need it to be continuous, right? So there are some theoretical applications, but a lot of applications are actually applied. Actually, where you're actually doing some computation. So you might, for example, in differential equations, there's lots of differential equations that transform nicely under biholomorphic maps. And once you have a disk, it's much easier to work in a disk than it is to work in a sort of a complicated domain. So you might as well try to get everything into a disk. Now, having an existence statement is not very useful, right? Or having this thing, well, you can find a sequence that maximizes the how do you actually explicitly do that, all right? So having an exact equation would be useful, and the theorem, of course, doesn't really tell you that, right? It doesn't give you any construction. It just says it exists, right? So there's actually lots of work, there's lots of literature on constructing these maps. Right. So, for example, if you use a polygon, there's an explicit formula. It's a little nasty, but there's an explicit formula for what the mapping is. So for lots of specific domains, there are people have constructed explicit formulas. So that's how I got the picture in the beginning, right? So. Another remark is that, and that's also useful, when you're maybe solving differential equations, is it doesn't, or at least this version of the theorem, it doesn't tell you anything about how nice the map is, how regular the map is up to the boundary. Like, is it continuous up to the boundary? That means, is it continuous on the closure of U, right? Or does it extend to be continuous on the closure of U? Does it extend to be smooth? Does it extend analytically past? So the answer is actually yes, as long as the boundary of U is nice enough, right? So generally, the map is going to be as nice as the boundary in a vague sense, right? So you're going to have a nice smooth boundary. The map is actually going to be nice and smooth. All right. So let's look at look at some exercises that might be that are direct applications of the theorem. So first, you've seen this before, for a disk, right? I mean, we've actually used basically this the way to prove this. We have a construction for the automorphisms of the disk, right? Well, by this theorem, you really have automorph. Well, I mean, up to knowing what the Riemann mapping is. You sort of know a lot about automorphisms of any simply connected domain because it's just biholomorphic to the disk, right? So, for example, if I have any simply connected domain, there is an automorphism, so there's a biholomorphic map from U to U that takes one point to the other point, right? All right. Now, another exercise. So suppose that we have that. So again, we know this for the disk, and you can and by the way, maybe I should mention that because here we're going to assume that U is not C. Here we didn't assume it, so you have to work in cases a little bit. But here So suppose that U is not C, it's simply connected, and I have two distinct points, P and Q, and I have a holomorphic map that fixes those 2 points. Right? Then prove that it's just that F is just the identity. You cannot fix 2 points by a holomorphic map from U to U. And now find a counterexample for this if U is C. So if U is C, you can fix 2 points. So find 2 points and find a function that fixes them, which is not just the identity. All right. Now, another thing that you can say, well, okay, so we have simply connected domains. So how about domains with holes? Okay, so the answer is actually, a little trickier here. So, for example, if I take the punctured disk and the annulus, the domain between the circles of radius 1 and 2, those are not biholomorphic, right? These two guys. So prove that. Prove that these are not biholomorphic. Right? There is no biholomorphism from one to the other. So you don't have a similar theorem or a similarly simple theorem, right? Like let's say that every domain with one hole would be, biholomorphic to, let's say, the punctured disk or an annulus or something. It's not true. So, all right. I mean, there is something true, but you have to. Anyway, we're not going to worry about it. let's say that. But like different annuli are not biholomorphically equivalent, really. All right. So suppose we have an entire function, so entire holomorphic function that is injective. An interesting application of the Riemann mapping theorem, because at first you might see, where does the Riemann mapping theorem come in? Because I'm talking about functions just on all of C. But you can prove that that if you have an entire holomorphic function which is injective, then F is onto, right? And the proof does use the Riemann mapping theorem. So, all right. So that's a nice exercise. So next time we're gonna skip to 6.3.3. I'm gonna skip 6.3.2. It's an optional section, and we're gonna prove basically a thing that I postponed before, that you can always find, given any compact, you can find a cycle around it, and it's actually a little bit of an annoying thing to prove, and there's a bunch of ways to prove it. And well, you can use the Riemann mapping theorem. You don't have to, but you can use the Riemann mapping theorem to prove it. So we're gonna do that, and that's gonna be the final thing that we needed to prove one of the characterizations of what simply connected domains are. All right. So that's next time. So see you then.